Okay. Okay, so let's see. Okay, so let's continue with this. Okay, right. So last time we defined the tangent space to a point in a manifold. We have two distinct approaches. One of them has the algebraic one, which consists that a tangent vector is identified with a derivation on the algebra of germs of a function. And the other approach was using curves, like the tangent vector to a curve. So now we are going to define the differential of a smooth function. And this is what we have now. So we would consider a smooth function. And I'm going to take a vector. So on all of this class, I'm going to consider only a vector, not vector fields. So I only care for one single vector. Okay, and I'm going to look at this. So I'm going to define this function. Here, note that f is a function on n, not on m. So to every function on m, I'm going to define this, right? Now note that so I have m, n, this is f, and then I have small f. So this is the composition that I have here. And I know that x is a derivation because it's in the tangent space, right? So what I claim is that this definition makes y into a derivation on this space. Okay? That's our claim. So I'll start with a derivation on m, and using this function f, I'm going to define a derivation on n, and more explicitly at the point f of p. Okay, so let's prove that this is a vector in the tangent space. In other words, is a derivation. So remind me, what is the definition of a derivation?
Linear map that satisfies this dynamics rule or the product rule.
Right. So I have here exactly just showing that this is linear on the functions. I didn't work out the scalars, only the sum of functions. So I have here the definition of y, and then this composition breaks has the sum of these two compositions. X is a derivation, hence it is linear. And then again, I use the definition of Y. And that's how I improve that Y is linear. And so I didn't work out the details for the scalar, but it will work the same way. And for the product rule, so again, I have f and g, the functions. And also, I mean, to be more precisely, I'm avoiding to put the square brackets, right? Remember that this is a quotient. So I'm just writing down the function everywhere. I'm omitting the brackets, but keep in mind that they are equivalence classes. So first, we apply the definition. And then again, this will give me the inside part, the product of the compositions. And now we use the fact that X is a derivation, so it satisfies the product rule that goes like this, right? So remember that in the product rule is where this point becomes important. So I have to evaluate at P each function. And that's what I have, right? Because X is a derivation at P. Okay, now. So using the definition of Y, we get this. So it follows that this definition makes Y into a derivation on the terms of functions at f of P. Right, so we have a derivation. This is true. So as before, if I have a function and a point on the domain, we are going to define the differential of the function f at the point P. And it's going to be a map between tangent spaces, the tangent space at P and the tangent space at f of P. And it will be defined exactly as what we have before. It will be X okay? By the above computation, this is a derivation, so it belongs here. And that's the definition of this new vector. Okay, so every time that I have a smooth mat, I fix any point, any base point on the domain, and I will get a map between the tangent spaces at P and at f of P. The definition is given by this formula here. And this is what we call the differential of f at P. Okay, this is also sometimes called the push forward of vectors. So a vector is pushed forward. from the domain to the codomain of the function. So that's why it is the push forward, right? Okay, now here I want to stress this word here. Last time we ended the class with the definition of a vector field. But we push forward only vectors and not vector fields. And why is that? I mean, because F could be non-injective. Okay? So Q can go here and P can go here. And so I have a vector here, another vector here. If I push forward any of the vectors, I might get this, and I might get something like this. So at one point, I have two vectors, and that's not a vector field. So that's why I want to stress that we are taking this only on vectors and not vector fields. Okay? On the domain, there's no problem. I can take a vector field. And once that I push forward every vector, on the other side, I might not get a vector field. Because in one point, I can have more than one vector. Okay, so we are only allowed to push forward vectors and not vector fields. Now, something more important about this is that it's not only a map between tangent spaces, but it is actually a linear map. Hence, if you have a smooth function between two manifolds, and you fix a base point on the domain P, you will get a linear map. Okay? Which is the differential of the point. Okay, so, there's a typo here, so it should be f of P. Okay, this is there. So at every point in M, I have a linear map, which is the differential. Good. So this is like the important concept that we will try to get used to. I'm not going to prove the proposition that's left as a homework problem. You can check that it is linear. It is a very important thing, to realize that it is linear. But I'm going to focus instead on trying to understand this. This is in some ways something that it is not new for you. You have seen this one way or another, and we will make some examples of this. So I'm going to take a smooth functions between R1 and R2. Okay? So you might write the function as C1, comma, C2. And remember that in order to talk about the differential, we need a base point. I'm going to take the 0 in the reals. Okay? So I have something like this. So remember that we have the 0 here. And we have the differential, right? This is what we learned. It will go from here to here. Here, we have a generator. That's what we saw yesterday for the tangent space, a basis. Remember that on Euclidean space, we have a canonical coordinates functions, and that will give me a canonical basis on the tangent space at each point. In dimension 1, usually we write d over dt instead of d over dx. So here, I have the vector, which is d at 0, which relates to d of x1 that we saw yesterday. In R, usually we use t instead of x. So for the time being, just think of this the way that you thought about this in calculus. You have a curve, and then you take the derivative, and usually you will say that, okay, so I will get this the tangent vector to the curve. So you are moving here, you describe this curve, and then you compute this vector. How do you compute this vector? Do you remember?
The tangent one?
Yes. So you have this and this.
The derivative over the norm.
The derivative and what else, Moises?
Over the norm.
No, but I mean, we don't need to normalize, right? I mean, what you do, you take the derivative of C1 with respect to t, the derivative of C2 with respect to t, and usually when you evaluate at the point t equals 0, this is the vector, but we usually think about it, we would translate it to the point, right? Remember that this is C of 0. So I mean, this is in the notation that I just defined above about the differential. And I'm going to show you how to compute this. Or also this, okay? So you know that this vector here is the one that I have here. And we are going to push it forward, it will be a vector on the tangent space of this point. But there, remember from yesterday that we have a basis for that vector space. This is one generator and this is the second one. So I know that this vector lives in that vector space. I have a basis, so I only need to know what is A and what is B. Those two real numbers. Okay? So that's the problem. So I need to find what is the value of this number, and by doing so, I know what is the differential of this. And the way to compute these numbers is as follows. So this is a derivation, this is a derivation. I'm going to evaluate it at one function, but one function that it is useful for me. And that will be the function R1. So the projection to the first entry. Because this will give me 0, and this will give me 1. And so I know A. Right? So I'm going to evaluate this differential on this function. Now, so this, I can just open the sum. And do you agree that this is equal to A1? Only this part. Right? The derivative of R1 with respect to R2 will give me 0. And the derivative of R1 with respect to the R1 variable will give me 1. And so I only get A. Is that clear? Now, let's work out the left-hand side. What about this? Here we use the definition of the differential. So this is going to be okay. But remember, remember how do we wrote down C? If I compose with R1, R1 is the projection of the first coordinate. So this is the derivative with respect to t of C1 evaluated at 0. So you have A is equal, similarly, you will get B is equal to this. And so you have just computed the differential at 0. So, well, let me write it still. I was going to avoid the base point, but let me put it. So this vector is at x naught. And then v was the derivative of C2 evaluated at 0. Okay? And I mean, this is what you do in calculus. You have this curve, and then you want to know what is the tangent vector at a point. So you just do this, right? No, sorry. That's the tangent vector to the red curve at the point C of t. So once that you take t equals to 0, you are here and you are here. So this is what you used to do before. And in this new language, it's exactly the same, but now written this way. Note what is the number here and the number coincides with this and with this. Clear? Okay. So here, it was crucial what we did yesterday, that we have a basis for the tangent space. So because I know that this is a vector, so and I have the basis, so it only remains to determine the value of the scalars A and B. Right, so any question? You're okay? Great. Well, let's look the other one. So I'm considering now this function. So we're going to compute the differential at a point and see that it is very much related to what you know from multivariable calculus. So I have f as smooth function between Rn and Rm, And so I write, oh, let me just be consistent with this. I don't know if I put lower or upper indices. So let's say this, right? So I have this. I put F1 up to Fn, the coordinate functions or of capital F. And I want to compute the differential at this point of this function. I make a base point P on Rn, and I want to compute this. Again, we will use the fact that we have a basis here and here, right? We have the canonical basis. And then you know that this is a linear map. So if I have a basis here and a basis here, we are going to write down the matrix of that linear function with respect to those two bases. Okay, so for this example, I'm not going to use the Ri's as coordinate functions because I have two Euclidean spaces. So I will use the x for Rn and the y's for Rm. That's going to be my coordinate functions. I'm going to avoid the Rj's. So in order to understand this linear map, I'm going to take only a basic vector and compute its image. Because I'm using this is part of the basis, right? You know that these vectors here form a basis of the tangent space at P. So I take one of them, and I know that the image is going to lie here. I also know what is a basis there. So this vector looks like this. And again, I need to find the value of those M scalars. So little by little, I'm going to be omitting this, right? Remember that this is supposed to be at F. Similarly, this. So I'm going to start to avoid that, and this is at P. But keep in mind that there is a point of reference in all of this. Okay, so I used the same trick as before to determine the value of Aij. So on this side, I'm going to evaluate at the function yi, which is a smooth function. All of them will vanish except when I have an I here, which is going to give me 1. So on the left-hand side, I have this. And now I put here the right-hand side. I go through the definition of the differential, which is this, right? Now, remember, what is this? F is a function from here to here, while I is the projection of the I entry in our M. So, this is equal to Fi. So we know what is the value of this constant. And it is given in terms of the function, in particular of the entry Fi. So this linear function with respect to this basis and the corresponding basis here is nothing new. It's something that you already know, and it is the Jacobian matrix. So the differential of a smooth function between manifolds generalizes the concept that you know about the Jacobian, right? And remember from multivariable calculus, so at each point of the domain, you have a matrix. So when you vary the point, the matrix varies also. Now, just to finish up with this example, this is F. So the Jacobian is a matrix of what type? Is it a square matrix?
Not necessarily.
And so the answer is?
Nope.
So it is a matrix of what by what?
M rows and N columns.
So M by N? And it should be clear also that we are with real scalars, right? Okay, so this is the differential that we defined before for smooth functions is a generalization of the Jacobian matrix. Okay, now let's do one more example. Take the identity function on a smooth manifold. And let's compute the differential of this function. It's going to be a linear map between this and this. The same vector space. So let's do the definition. I take a germ of functions at P, and then I apply this. I have here the definition. But F composed with the identity is exactly F. So we have it here. That's the differential. In other words, the differential of the identity is the identity map on the linear space, on the tangent space. Right? Okay. So we have seen the differential of a smooth function, and it generalizes the Jacobian of Euclidean space. Now, so by this, all of your knowledge and intuition of multivariable calculus of the Jacobian matrix, it is straightforward to try to understand the chain rule. So, do you remember what is the chain rule in this context of multivariable calculus? Okay, so what we will get now is exactly the same that you get on multivariable calculus regarding the chain rule. So let's consider two smooth functions so that we can compose both of them. We have already seen that the composition of smooth functions is a smooth function. And the whole idea is to look at the differential of this function in terms of the differential of this and of this. Okay? And whatever relation we get is what it is called the chain rule. And the chain rule is exactly this. So I have P is in M, and I'm computing the differential of this. So this is going to be the differential of F at P composed with the differential of G, but at the point F of P. Right? So this is the chain rule. So it is the composition of two linear functions. And the question that I made a few moments ago regarding the chain rule in this context, so do you remember it was just the matrix product? That's what you see in multivariable calculus regarding the chain rule. The product of the Jacobians. Okay, so we're going to prove this, and it is a very nice proof, straightforward, and it is just a computation. So, right, I'm going to take a derivation at M, and when I apply this, I get a derivation on P. That's why I'm taking F to be a smooth function on P. So the first thing is just the definition of the differential. I have the vector and this. Okay, now let's work on the other side and see that we get the same. So we have the same x and the same f. Right? But this, it means first push forward with respect to f, and then push forward with respect to g, and then you evaluate the function. Right? But now, let's apply the differential definition here on g is lower star. So this is my x, and this is what I'm putting here, right? The definition of the differential, like the one that it is here. And then you have to compose these two and put it here. So if this equality okay for everyone?
Can you repeat it again, please?
Right, so this equality, I'm just going to apply the definition of the differential. So let me write it here with some other function. H, lower start, this is my definition of the differential, right? So let's identify all of this. This is H star. This is Y, and F is F. Then, so let's look at this. I have to put Y first, but Y, here it is, F lower star of X. That's Y. And then I have to put F composed with H. That is F composed with G. So this equality is applying the definition of the differential here. Moises?
All right.
Okay. Now, again, let's see our result to see that everything makes sense. So X is a tangent vector on M. Then all of this is a tangent vector on N. And the base point is going to be f of p. Now, if I'm saying that this is a tangent vector on N, I need to have a germ of functions on N. And yes, because the domain of G is N, and then I go to the reals by F. So it makes sense, right? This is a real value function. on n, and this is a vector on n as well. Okay? Now let's move on. Again, I'm going to apply once again the definition of the push forward, but now on F lower star. So I have this now. Right, so this is Y, all of this is F, and this is H. If I apply just the definition of the push forward, I get this Y and that composition. And indeed, right, these two are equal. And so we have the chain rule. Any questions? Okay, then, so let's move on. So the reason that I wanted to put this is because in some way it is an easy proof, but also it requires you have a good knowledge of what is the push forward or the differential to understand very well the definition. Right, so this is fundamental here. Just the definition of the push forward. Okay, so now that we are done with the chain rule, let's look at diffeomorphisms, right? So I have a diffeomorphism between two manifolds. That means F is smooth. Always all of our functions will be smooth. It is bijective, and the inverse is also a smooth function. Right? Then I can look at the composition. It's the identity map on M. And now let's compute the differential of this. On the left-hand side, we're going to use the chain rule. So the differential of this is here by the chain rule. And we already did the example of what is the differential of this map. And it is this. Right? So from this, I get this. Is there any questions up to this point? Okay. Now, perhaps it is important to mention this. Again, this is just an observation from multivariable calculus. So if you have a function from R to R, a function from calculus 2, you compute the derivative, right? And that's a number. In this language, you have a 1 by 1 matrix. Okay? Now, basically what you study about this are two things. Is either A is 0 or A is non-zero, right? If A is non-zero, what can you say about the function near the point x naught?
That it should have an inverse close.
Right, so you have a local inverse, right? Right, so here, here is when you say that x naught is a critical point, and here, so you at least know that the graph, I don't know how, but you have an inverse, as you are saying this. A local inverse. So this is local information. Now, what about in higher dimensions? For that, you need to perdí mi pantalla. Ahí está ya. Muy bien. So now you look at something like this. N and M are equal. So you have a base point and you compute the Jacobian. I don't know if you use this definition for the Jacobian. So this is an n times n matrix. And now, the way that you move is not if the Jacobian is the zero matrix or is not the zero matrix. What is the right statement of this in this context?
It's about the determinant now.
Right. So you care about the determinant. And so in this case, you get the same conclusion as above, right? So what we are doing is exactly the same for a function f of the same dimension. Because in this case, you have this map. So this is a linear map between a vector space of dimension n and another vector space of dimension n. To talk about the determinant, and I forgot to say it here, I mean, well, no. So this is a linear map. Regardless of which basis do you take on the vector space, the determinant will always be the same if it's zero or non-zero. So you care if this map is invertible or not. If this map is invertible, corresponds to this case, and locally f is going to be invertible. Okay? So this is what we are measuring with these linear maps. The same way that you were measuring here on Euclidean space. So that's what I was having here. It should be no surprise that this map is non-singular, because we already know that f is globally has an inverse. Right here, this is a global inverse. So we expect that linear map to be invertible. Okay, so this is the conclusion of this. Determinant non-zero, meaning an isomorphism, linear isomorphism. Okay, now remember always this is giving us information about the function, but only near P. So the differential tells me something about the function locally at P. And with this, we can now prove in a very easy way a very strong result. Something that we used before. If two open sets of Euclidean space are diffeomorphic, then the Euclidean spaces must have the same dimension. Remember that we use this in our concept of dimension of a manifold, right? We have two shards. If they have something in common, they must be shards of the same Euclidean space. We used that a while ago, but we didn't prove it. We only managed to distinguish between dimension 1 and the rest. And remember that we use a concept, it relied on a concept of topology, whether a space was connected or disconnected, right? But now we can prove this in full generality, no matter the value of M and M. Good? Okay, so let's prove this. Because U and V are diffeomorphic, there's a smooth function, a smooth diffeomorphism between the two, right? Okay, now. And that's why I have the previous observation. So this is a diffeomorphism. That means at any point, this is a bijective linear map, right? So hold on. Okay, now we are back. So sorry for this. So again, we want to group the invariants of domain of the dimension. So again, I have U and V open sets which are diffeomorphic. So we said I have a function f which is a diffeomorphism. By the above observation, the linear map at any point, regardless any point on U, this is going to be a linear isomorphism. But you know from linear algebra that the dimension is the only invariant of a vector space. So these two have the same dimension, because you have a linear map between those two vector spaces. They are isomorphic, they must have the same dimension. So that's a proof, a very nice proof of this result. Okay. Any questions? Okay, now that we have proved this, let's wait. Let me also give you the sketch of another proof. If you have a diffeomorphism between U and V, because U is open, take a small open ball and not consider the interior, only the shell, the sphere. So if you have a diffeomorphism there, you get U is in Rn on the sphere, which is the boundary of a small ball, to the image, you get this homeomorphism. So now we are on topology. If one mole is diffeomorphic to the other one, remove the interior, so you have the boundary of the ball is homeomorphic to its image, which is going to be another sphere. And here you use algebraic topology to conclude the proof. So this is more or less what we did last time, in the sense that instead of this, I have an interval. So I want making like the full ball, and on the other one, I remove the center, one becomes disconnected and the other one not, right? This is for dimension 1. An open ball in R1 is an open interval, and I take the midpoint, which is the center. Disconnected, the other open ball is not going to be disconnected if the dimension is greater than 1. Now here, you use algebraic topology in particular, so you will use homology. So if you have that map, you get the induced map in homology. And this is very similar in spirit what we did before. If you have a homeomorphism here, this map is going to be an isomorphism. And that's how you get that n minus 1 must be equal to this. So using algebraic topology, in particular the concept of homology, you can also prove this. Okay, now so let's move on. Now I'm going to talk again about the differential, but a different way of computing the differential, right? So far, we only have the definition, but now we will find another way to compute this in more or less a geometric approach. So first, I'm going to stick with Euclidean space. So on Euclidean space, I take a point and a vector, a tangent vector. For instance, that one there. So this is a tangent vector. Because we are in Euclidean space, we have the canonical coordinates, R1 up to Rn, and also I have a canonical basis on the tangent space. Okay, now so this is Euclidean space, and that's why I can propose to you this problem. Can you find a curve such that at 0 equals the base point P and the derivative is x? Where x is given by this, or if you prefer, I mean this is a1, but when you think about as a vector. Jesus, any ideas? Let's say, what about if x is this only? What's going to be a curve such that the derivative at the origin will give me that vector? Can you come up with an example?
Maybe something like the identity.
I don't know. So tell me, what is C of t?
Let me think.
Okay. Let me move aside here. And only in 2 dimensions. I want a curve from the reals to R2. At 0 is the 0 vector, and the derivative of 0 which is the same this vector. What's an example of that curve?
Something like t comma 0.
Come again?
Yeah, like Moises says t
Yeah.
comma 0.
X, but I mean, I don't get it. What is the but it needs to depend on t, right? So instead of x, t comma 0, right? And exactly, this will work, right? On 0 is equal to the origin, and the derivative is exactly v over dr1, that vector, right? In fact, for this example, at any point, this unit vector will be the derivative, okay? For this particular example. Okay. So I want to do the same problem, but more in a more general setup, but the same way of thinking will resolve this. I want this to be the derivative of 0, right? So it is exactly this, right? Before what Moises example, so this is 1. In our previous example, all of them are 0, and the b is 0. All of the b's are 0. So it is the same answer as the one that Moises gave. So this is the example that we want is a smooth curve at 0 equals p, and the derivative is constant, in particularly at 0, because I only care about the derivative at 0. So let me make that more precise here. This is true, but we only care on 0. Exactly this. Okay. So this is what you have solved. Given any tangent vector, you can find a curve such that the derivative at that point is that vector. So this is in Rn, and you can solve this also on a manifold, because this is local. So you just have to do it on a chart. Okay? So the above example holds also on an arbitrary manifold. Right? Now, I'm writing this in terms of instead of C dot, because now we are on manifolds, but it is exactly the same. okay? I'm not going to prove this, just sketch a proof, a drawing of it, because you're given this vector, then pick a chart, any chart, and here you have the function, right? Now, this function is smooth on this open set. In fact, it's a bijection, it's a diffeomorphism from this open set to some open set on Euclidean space. So that means that here is a linear isomorphism to here. I have a linear isomorphism with the tangent spaces. Hence, because this is a linear isomorphism, I have a unique vector here where this one goes, right? So that's how we lift this vector to a unique vector here. But here we are on Euclidean space. And here, you know how to solve the problem. You already did. So once that you have here the curve, that means that you have a function from R to this. What do you do next? You compose with the chart map. And that will give you a curve on M. And that will have the desired tangent vector. Okay? So you solve the problem upstairs on Euclidean space, and then you push it down on the manifold using the chart map, phi of u. Okay. So this is just a sketch. Is this idea okay for everyone? Great. Okay, so let's move on. And this is what we were aiming at. Another way of computing this using a curve. Right? So the problem is, I would like to compute the push forward of a vector. What do? I consider a curve that goes through the point and the derivative is that vector. There are many curves. I take any one of them. And then I claim that the push forward is going to be exactly this. Okay, let me first do a drawing here. And this is x. I want to compute the differential of p of the vector x. So how do I compute that? I say, take any curve in M whose tangent vector is x. Right, so this is C. It goes from some interval in the reals to the manifold. So in order to compute the push forward of the vector x, what I'm saying is, well, once that you have that curve, you have another curve on N, which is F composed with C. That will give you a curve that goes through f of p. And then just compute the derivative there. And that is going to be the push forward of the vector x. So I have x, and this will give me the push forward at the point P of x. Okay? That's what this proposition is saying. How to compute the push forward using curves. So let's prove this. So this is the notation that we have from calculus, which agrees to this one that we have seen today about the differential. Okay, so let's see. So here C is the one from the hypothesis. So instead of x, right, we know that this is equal to our vector x. Instead of x, I'm going to write this right there. And now, this is just the composition of this, as we saw a while ago. But this is precisely using the chain rule. It is this. And then use the definition of the push forward using this function. And you get this. Okay? And also the formula is saying that it doesn't matter which curve that you take, as long as at 0 equals p and the derivative at 0 is x. Here, on the left-hand side, we don't use c, but here, the curve appears. So we don't care which one do we use. So this is another way of computing the differential via smooth curves. So a geometric way of this. Okay, now, so, right. I'm going now to compute the push forward of some other maps that they are more or less very close related to multivariable calculus. So I have a Lie group. So remember that we have seen the definition of a Lie group. That is a manifold. So it is a group that it is also a manifold, such that the product is a smooth function and the inverse operation is also a smooth function. Now, on any group, we have a distinguished element, which is the identity element. So if I look at the tangent space at the identity, this space is what it is called the Lie algebra of the group. So the tangent space at the identity is the Lie algebra. So remember that an algebra is a vector space that in addition has a product operation. So far, we know this only has a vector space of the same dimension as the manifold G. Later on, we will see what is the product on this vector space, so that it justifies the name of algebra, the Lie algebra of the group. The common notation of this is a G. I think it is the got it font that you use. So this is the Lie algebra. It is a finite dimensional vector space, the tangent space. So for instance, let's be more specific. For G, take the linear group. We have seen that this is a group. It fits inside the Euclidean space, where the Euclidean space is identified with the set of n by n matrices. It is convenient, and especially in Lie group theory, that the space of n by n matrices, it is called the endomorphisms of Rn, linear maps from Rn to Rn, singular or non-singular. So this is the endomorphisms. And remember what we have seen. This is an open set here. So the tangent space here is the same as the tangent space there. Okay? So the tangent space, the Lie algebra, we write it like this, is the tangent space here. But because GL is open, this is the tangent space of the Euclidean space, Rn squared. And Rn squared is the same as the endomorphisms. Okay? This is clear? Now, so the endomorphisms of Rn is just a linear map between Rn and Rn. in this particular case, the product operation is decomposition. So you have two linear maps. Then decomposition is the product when we have the algebra. So this is the Lie algebra. Of the group of non-singular matrices is the endomorphisms. It is a linear vector space of dimension n squared, and the product is the composition when you think about them as maps. Okay? Now, again, this is just the justification of this in this particular case. Later we will define the algebra or the product structure on that vector space. So let's stick with this group, the linear group, right? So you have this, and you have two operations, multiplication on the left or on the right. So we fix a matrix, a non-singular matrix A, and then we have two operations, this one and this one. Because GL is a Lie group, these two maps are smooth. But I mean, you can just check that they are smooth because they are polynomial functions on the entries. It's just the matrix multiplication. So the goal of all of this is to compute the differential of these two maps. Okay, so remember that this is the non-singular matrices. So let's compute the differential at the identity. So this is what I would like to know. Okay. Remember, A is non-singular, and this is the set of all n by n matrices. Okay, so I want to compute that differential. So I take any x, a vector on the tangent space, and I know that the tangent space is the set of all n by n matrices. So keep in mind that x could very well be singular. That's no problem, because x is on the tangent space, not in the group. So we will use the last proposition. I will take any curve here, and this you can do explicitly because GL lives inside a Euclidean space. I take any curve that at 0 is the identity matrix and the derivative is x. So here I'm using the last proposition to compute the differential using the curve. Now, what is this? This here, This is composition, right? That's the definition. Okay, so that's the definition. Now let's use the definition of the map LA is matrix multiplication by A on the left. Remember that C of T is a non-singular matrix because C of T is in here. So this is matrix multiplication. So I'm taking the derivative of a product of two matrices. The first one is independent of T, and the second one depends on T. And I have to evaluate at T equals 0. So you can check that this is precisely just the derivative on the second factor and evaluating at 0, which is x. Okay? So the differential of the left multiplication by the non-singular matrix X is also matrix multiplication. So that's the concluding remark. But I just want you to keep in mind that it is something very different. Okay? This product is different from this one here, because this is the product on the group of non-singular matrices. A and B are non-singular. And this product here is the product of n by n matrices. X can be singular. For instance, X will be the 0 matrix. And there you have the differential. In a similar way, you can compute the differential of the right multiplication by A. Okay, so this is the conclusion of all of this last part, which is related to Lie groups or a particular group, just GLN. And how to compute the differential, but using curves. Sometimes it's more efficient to do it that way than look at the basis. Great. Are there any questions?
No, that's fine.
Right, so we have seen the, let me just to wrap up things. So I have a manifold and a point, and I get a vector space. Well, we will always have a base point. So for M, I have this. If I have a function, I get this linear map. So from something smooth, we are going to something linear. This is local information. Sometimes this is called infinitesimal aspects of the function f. Or if we are in the first setting, the infinitesimal aspect of the manifold at P. So from differential geometry, we are jumping to linear algebra. Right. So that's about it. So we are done for today, and we'll continue next week if there are no more questions or comments.
What do you mean by the infinitesimal aspect of this?
Right, so the infinitesimal means exactly this. Is when you go, so infinitesimal is a local thing, going from a point to this. So instead of having something curved, so to speak, in the manifold, you go to something straight, which is the vector space. So you, that's more or less what it is called, the infinitesimal thing of the manifold. And also the whole idea is that locally on the manifold about P, more or less you can understand what is going on there on the manifold if you go to the a neighborhood of the origin of Tp of n. And it is very much what you have in calculus. So you have the function, the graph, and then you take a line. So the tangent line is the linear approximation to the graph. So in that way, it's more or less said that the infinitesimal aspect of the manifold or of the function in the second point that I have here. Now, I mean also, again, in calculus, you have this, right? So the derivative is the infinitesimal aspects. When you were in calculus 1, you study small increments, say the infinitesimals. And remember, this is the derivative of the function. Like we already saw, is the Jacobian when m and n are in Euclidean space. The Jacobian at a point. So that's also the relation with the name infinitesimal, like here in calculus 1. The small increments of the function.
All right. Thanks.
Okay. Any more questions? Okay, then, so I will see you next week. Right?
See ya.
Yeah, see you all.
Next weekend.
Bye.